In this lecture, we are going to talk about the basics of computer design, and we will focus on the data path. Here you can see an overview of a CPU design. We can divide the whole CPU into three main parts indeed. The first part is called the data path, which is as I mentioned, which is the topic for this set of lectures. And data path is where all the actual data processing is performed. The next part is the instruction set, which is the interface between the programmer and the CPU. When you want to tell the CPU what to do, you do it through the instruction set indeed. And then we have the control unit, which uses the program that is provided by the user. So the programmer's instructions are used by control unit. And then the control unit tells the data path what to do. Okay, so which operation to perform is determined by the control unit. And then the data path will follow it. So as I mentioned, we will look into the details of the processor's data path. The control unit and the instruction set would be considered later indeed. And the data path will be responsible for doing all the operations indeed. It will have an ALU or arithmetic logic unit, which performs the computations. A limited set of registers will be also available with the data path, which are used as fast temporary storage. And there will be a larger but slower random access memory working within the data path. So the CPU consists of all those three, mainly the ALU, mainly the data path, the instruction set, and the control unit. For our data path, as already mentioned, we will have the arithmetic logic unit, ALU, which is connected mainly to a set of registers. However, for the CPU itself, we can look at the CPU in the form of a big sequential circuit. And we can say that it is basically moving the data between the registers by performing some arithmetic logic operations or ALU computations. Some of the registers are used in order to store the values which form the state, and the ALU, the arithmetic logic unit, performs various operations on the data stored in the registers. So regarding our data path, here we have the guiding principles for basic data path. So we are focused on a basic data path. What we need to have for a basic data path is first a set of registers. Okay, so we will have a set of registers in the form of a collection of individual registers like R0, R1, R2, and so on and so forth. And also a set of registers with common access resource, which is called as register file. We will come to this register file later. We will cover it later. And then we may have a combination of the two that we just mentioned. In order to implement the micro operations within the data path, one or more shared resources for implementing micro operations will be used. There will be buses, which are used in order to transfer the data among the registers from register to the data path to the ALU, and from ALU the output that we get from ALU back to the register, to a given register. Obviously, we will need to have the arithmetic logic unit, which is where the operation, the micro operation, is performed. And we also have a shifter, which is used in order to perform some shift operations whenever needed. Here you can see an example of a data path. You can see the internal structure indeed. This specific data path consists of 4 parallel load registers. The 4 parallel load registers are here: R0, R1, R2, and R3. You can see that the data input to all these 4 registers comes from this bus. Okay, so we have the D data, which is connected to the input, to the data input of all these 4 registers. They also receive the load command. So for the load command for each one is separate. So whenever the load to any of these registers becomes true, then the register will be loaded with the data which is available on the bus, on the data bus, as we have seen over here. Then we have 2 multiplexer based register selectors. Okay, to perform the operations, we need to select among these registers. For that reason, you can see that we have 2 multiplexers. This is a 4-to-1 line multiplexer. This is another 4-to-1 line multiplexer. Both of them are connected to the outputs of data output of those 4 registers that we had. So it's the same for multiplexer 1 and multiplexer 2. And the output that we get from the output line that we have for the multiplexer are available as data for, as we call them, B data and A data. Okay, so what we get from the multiplexers, from these 2 multiplexers, will be B data and A data. And you should, by looking at this, you should know that A data could be R0 or R1 or R2 or R3. So any of those could be in A data, and similarly for B data, it could contain R0 or R1 or R2 or R3. Which one to include will depend on the select input to the corresponding multiplexer. So you have A select and B select in order to determine which of the input lines to be transferred to the output line of the multiplexer. Then we have the register destination decoder. Which is here. Okay, so we have the decoder over here. It's a register destination decoder. It's a 2 to 4 line decoder indeed. So this is 2 to 4 line decoder. Based on what we have at the input side, one of the outputs will be 1 and the rest will be 0. And as a result, if the load enable that we have here, which is indeed the write command, is 1, then the output of one of these ANDs will be equal to 1 and the rest will be equal to 0. And as a result, the load input to one of the registers will be equal to 1 and the rest will be equal to 0. So I can give you an example. Let's assume that load enable is equal to 1. If for the destination select we have 0, 0, destination select, then this output will be equal to 1, the rest will be equal to 0. So we have 1 here on this line, therefore the output here will be 0, 0, 0, and only for the first one we will have load equal to 1. And as a result, R0 will receive data that we have here, okay, D data. What is that D data? It's the result that we get from the ALU. So it will depend on which operation is performed inside the ALU. But with the destination select, we determine that the result of the ALU will be loaded into one of the registers. Then we have mux B for external constant input. You can see it over here. Mux B is here. It is a 2 to 1 line multiplexer. 2 to 1 line multiplexer. One input to the multiplexer comes from the output of mux B. So from here, me just change the size. So one input comes from here, and the second input comes from constant in. So if for any operation we need to use some constant value, then we can pass that constant value using this multiplexer. So if we set MB select to 1, then the output on bus B that we have here will be that constant value. For this data path, we have the buses A and B with several with external address and data outputs. So we have bus A here, as you can see, and we have bus B here. Both of them are the output lines from the multiplexers, but working with the external memories, as we will discuss later. If here we have a memory, then the data on bus A will be used as the address, and what we have on bus B will be the data. Okay, so in this way we can write the data into the memory. Then for our ALU, we have the arithmetic logic unit, as you can see here, and we also have the shifter which comes with that. So the whole thing is called the function unit. And then we also have a max F with MF select to choose which whether the shifter or the ALU is the one from which we are going to take the data. Then we have another max here, max D, which is again a 2-to-1 line multiplexer, and it is used in order to take in some external data. So with max D, we determine whether we are interested in getting the data from outside or whether we want to get it from the function unit. For the function unit, we also have the outputs, the status bits indeed, V, C, N, and Z, overflow, carry, negative, and 0. We will discuss these status bit outputs later, but there is a logic within the function unit to generate these. So basically, this is the overview of a simple data path. Okay, just to give you an idea of how this could be, how the data path could be formed. Later we will see details regarding what we have inside the arithmetic logic unit ALU, and also for the shifter, how they could be formed, and then afterwards we will see how the whole data path could be created.